Good morning to everyone in the US and good afternoon to everyone in Denmark. I can see we have a couple of people on from other countries as well. So of course, hello to you too. Thank you all for participating in our webinar today on biogas, sustainable biogas. We are going to dig into the climate and environmental effects of biogas production with our lead presenter today, Henrik Møller from Aarhus University. This webinar is organized by Biogas Go Global, which is a triple helix partnership between the Danish Energy Agency, Food and Biocluster Denmark, and the Danish Trade Council in North America. My name is Cecilia Sørensen, and I work as a commercial advisor for the Danish Trade Council North America. I work in the team Waste, Recycling and Biogas with my colleague Chris Wohl, who is head of the team, and he is also on the call today. I'm also very happy to say that we also have our colleague from Danish Energy Agency, Jonas Jürgens, and Claus Mortensen and Michael Stückler from Food and Biocluster Denmark. So we are all on board to answer any kind of question you might have or that might arise. The Biogas Go Global project is a 3.5-year program that will end by March next year, so 2022. It has the aim of increasing the Danish biogas, increasing the growth in the Danish biogas sector by increasing the collaboration between our Danish and American companies, universities, public partners. But the partnership especially creates a lot of value for our Danish Biogas Alliance that we have here in North America. It currently consists of 6 companies: Ammonia, Biogas Clean, Gemid and Ecogy, Novozymes, LSM Pumps, and Renew Energy. And North America is a geographical focus area of Biogas Go Global, but we also conduct activities in other countries. And right now I know that some of the focus countries are Spain and the Netherlands as well. I know my colleague Claus will also mention this in a couple of minutes, but I just want to highlight it too, that last year we did launch this publication called Biogas Production, Insights and Experiences from the Danish Biogas Sector. And it has now been translated into 5 languages. So after this webinar, if you're interested in learning more about the Danish biogas sector, feel free to reach out to us. Then we'll share a link with you where you can get this publication, or where you can download this publication. A bit more practical, then you can see that we are using the Zoom platform, and below there's the option to raise your hand or to insert a question in Q&A. And please do, for all of us, but especially for Henrik Møller from Aarhus University, who is also one of the authors of the publication. We'll be happy to answer all of your questions, hopefully during the next hour. Now I want to hand over the word to my colleague Claus from Food and Biocluster Denmark. Claus is a business development and incubator manager, and also one of the people I know that knows the most about the Danish biogas sector. So over to you, Claus.
Thank you very much, Cecilia. I'll just share my screen here. Also asked just to give a short introduction to where we are in biogas in Denmark. So just before Henrik will give his keynote, can you see my screen now?
Yes.
Good. Yeah, so my name is Claus Mortensen. I've been working in the biogas sector for the last 10 years with R&D and innovation, but also commercial and export-related activities in several countries. So our role as in Food and Biocluster Denmark is to connect people between universities and companies and companies, both in Denmark and outside. So I'll just give you a short introduction to basically what we've seen in Denmark in the Danish biogas sector for the last, let's say, 7 or 8 years. There's been we call it a quiet revolution. Some would say it's a biogas boom. Here we are, Denmark, a small country, but a big food producer. I think we produce food for 15 million, although we are only 5. And I think one of the key aspects here is the link between agricultural policies and the willingness to create jobs in that sector and still maintain a high sustainability as a country as a whole. I think what emphasizes what I think is key to take away here is the green policies we have across multiple parties. When we do policies, we do typically across almost all parties in the parliament. And we also have a good tradition of working together, as Cecilia mentioned before, the triple helix cooperation. So between the Danish Energy Agency in this case and the universities that Henrik represent and the companies that are now in our network. So you see some of the goals here: climate neutral by 2050 and 70% in 9 years from now. And the agricultural sector is working really intensive to reach that. I think we tend to say that we can, with current technology, reach around 60-65% of the 70%, and the rest will be new technologies that needed to be developed by Henrik and his colleagues and demonstrated. You see all the dots here. The green dots are all the biogas plants in Denmark. Some of them, there are more than that, and you see the gas grid. And those two sectors are really closely linked, as you can see here in my just screenshot from last month. We are hitting around 22% of the gas in the grid is currently green. So this means that even though we have our own gas production in the North Sea, the increase from January 2019, that was around 9%. Now it's around 22% of the gas in the grid is green. We expect that to rise to around 30% by 2 years from now, and hit around 80% in 2030. There's a new tender-based support for biogas on the way in Denmark. It will be launched next year and will follow the next 7 to 8 years, which will support this. But mainly we see the increase in the agricultural co-op plant. So a typical Danish biogas plant is where you haul in manure, agri-waste, food waste, industrial food waste to this plant, typically handling around 150,000, 200,000 tons of waste, putting the gas to the grid, and using the dyed estate as a fertilizer on the field. So that's a cooperation between farmers and energy companies. So you see here also the graphics to the bottom left. That's what we use in our biogas plant. It's old figures, and actually the one on straw has been, I don't have the exact figures, maybe Henrik got that, but what we see is now an increase in the use of straw and an increase in the use of household waste. So that's where we see the development right now. And as you can see, since the old subsidy scheme came into place in 2013, we almost only produce gas to the grid. I wouldn't go into details with this one, but the Danish approach is a co-op way of producing biogas, several farmers going together, and also have part ownership in the plants. And as mentioned, also what is important to emphasize is that it is a part of the circular economy that we use the different resources we have, which includes food waste, which includes manure, and use that and replace artificial fertilizer, industrial fertilizer. Some of the key takeaways is that, of course, you need long-term contracts, both on the biomass supply, but also the dyed estate, and also the payment of the gas, of course. And then I think some of the lessons we've learned throughout the last 30 years is that operation of the biogas plant is key, and it should not be a part-time job for, let's say, a farmer. That's some of the key takeaways here. As mentioned before by Cecilia, we did this publication September last year. I'll be happy to share it, or you can download it on biogasgoglobal.com. It basically puts together all the elements that we and some of the experience we have from Denmark the last 8 years. Some of the things here listed. What are the environmental benefits? Henrik will come back to that later. Some of the pre-treatment technologies, how to make use of diastase as a commodity, but also how you integrate different renewable energies into the gas grid through biogas production and the CO2 that you typically ventilate when you upgrade the gas for the grid. That's some of the innovations we see. We'll be happy to share it. So do feel free to reach out. As mentioned before, Cecilia, we have a platform where we put people together in the States and in Denmark. And again, if you're looking for contacts, if you're looking for specific technologies, do feel free to reach out to us. And then I promise just to list some of the activities we have in the pipeline. We have two free webinars. Next week, we're going to talk about the opportunities within food waste and biogas and how that is one of the trends we see in Denmark. On the 5th of May, we have a presentation from a Danish Gas Technology Center, which will talk about the economy of scale in biogas production, because there's a huge economy of scale in the size of the plant that you can get the price for biomethane down. So sign up. That's Cecilia's email here, and that's my key to introduce one of the leading researchers within biogas in Denmark. Henrik B. Møller is a senior researcher at Aarhus University, the Forum campus, where he got his own biogas plant full size that he and his colleagues are working with. He will share some of the insights from a fairly new report on sustainability that they did together with the Danish Energy Agency. So Henrik, please share your screen, and the floor is yours.
Thank you very much, Claus, for the introduction. Can you see my screen now?
Yes, we can.
And you can see my pointer also?
Yes.
Yes, very good. And thanks for the possibility to tell about this Danish study in sustainability in biogas production, which was finished last year. The study was done by me and several co-authors with different research expertises, and my own background, as Claus told, was in the biogas, biogas sector, and I've been working with that for almost 30 years now. This study was done with support from the Danish Energy Agency in the Bioenergy Task Force, which is running from 2019 to 2021 to stimulate the development in the bioenergy sector. Let's see here. Why can't I change my? Let's roll down my screen. I don't know why. Oh, okay, now it's coming. Yeah, okay. The aim of this project was to quantify the positive and negative environmental impacts from biogas production from different scenarios, and it should be with the current technology in Denmark. Of course, the best plan, but not a future optimized plant, and it should be studied with different biomass inputs. And the thing we should evaluate from the biogas plant, that was how it affects the methane from manure management, where we see a very positive effect usually from biogas. We should also include nitrous oxides from agriculture. Then, of course, an important thing was the energy production from the biogas plant, the substitution of natural gas and other fuels in the energy sector. Then we should also look at the methane losses, because we'll always have some losses from the plant which can compromise the total balances. And then we should include the greenhouse gases by the transport of manure, because we have a higher transport when we have these big co-digestion plants in Denmark. For the environment, we should mainly look at the nutrient leaching, especially nitrate, and then we should look at air pollution, and here it's mainly ammonia we are looking at, and NOx from transport of the biomass. So Claus already told a little about the biomasses that is used in Denmark today. This is not including the sewage waste sector, but only the agriculture-based sector. And we are always we have a co-digestion plant. That means that we mix different wastes and byproducts from agriculture. And as you can see on a weight basis, the largest fraction is manure. And then the second largest is organic waste, which plays a major role also. Then we have some energy crops, but we have some limitation on the amount we can use for sustainability reasons. Right now it's 12.5% we are allowed to put in, but we are way below that. We are around 4% at the moment. Looking at the energy production from the different biomasses, it's a little different. And here we can see that manure contribute with less than half of the energy, but the waste contributes very much. And among that, also glycerol, which is a special waste with many Danish biogas plants uses. So all these different biomasses are important to look at in our scenarios, and the 5 scenarios that we looked at, that was a manure-based scenario with only manure, both liquid and solid. Then we had a straw plus scenario where we substituted the solid manure with straw instead. That's a little theoretical plan because we have no plants in Denmark with such a high share of straw. Then we had an energy crops plant, and where we have a quite high share of energy crops. We are going to 12% energy crops, which is what is allowed at the moment. Then we had a waste-based plant, which is looking quite much as the existing plant looks. But this kind of plant will be less and less because this amount of waste is not available for the coming plants, because this is a depleted source, because almost all waste today is recycled to biogas. Only thing where we still have some potentials is in the bio-waste, where we are still increasing the source separation of municipal solid waste. Then organic agriculture in Denmark is playing a very important role, and the organic sector has some challenges in securing enough nutrients for the cultivation, and biogas is a very interesting technology for the organic farmers, and we are seeing a quite big expansion in the sectors of organic biogas plants. So when we are making these calculations on environmental and greenhouse gas impacts, of course, the references, what is our biomass used for if it's not going to biogas? So that's very important to choose the right references. For the manure and waste, we have a storage in 9 months, and we spread it in the field with a ratio spread with injection in the soil, and with a fraction spread on top of the soil with hoses. This is necessary because we have a lot of winter crops, and we don't have really good technologies now that will not have a high negative impact on the crops if we inject in growing winter wheat, for example. For our maize, our energy crops, our references to maize is actually cereal, and so cereal is a reference, and this means that there's very little changes actually go to cultivate maize. So we don't really, in this study we are not including the land use changes that will happen by taking maize into the bioenergy sector and having less land for food production. So that's what we are looking at it at a national level. That was decided from the start. Glycerol we regard as being incinerated for energy if it's not used for biogas. The solid manure is stored in the field for a certain period with a membrane on plastic to avoid emissions of ammonia, for example. Our bio waste, the reference is composting. That's because we have very high ambitions in recycling of waste, and in future organic fraction of municipal solid waste cannot be incinerated. So the references here is composting. So from the energy and CO2 balances, we also need to make some assumptions. For the transport, we regard it as transported in big trucks, and we have a factor on 2.7 kilos CO2 per liter of diesel of CO2. For the electricity, we are looking at the Danish energy mix, and that is quite low emissions of CO2 because we have a high share of renewables, and because of this, the emissions from CO2 by energy we use for our process is quite low. Then we, in our study, we have an heat exchanger on the plant. This means that we are recovering the heat, and that's especially important because almost all Danish biogas plants, or at least more than half of it, is thermophilic. This means running with high temperature, so we have a quite high energy content in our digestate. We also look at a retention time on 45 days, but we also look at how it will look if we increase retention time. Upgrading it done with an amine scrubber. I'll come back to that. And then the energy for heating, we use natural gas, or actually we are, after upgrading, we use our own gas to heat our process. Yep. So gas production is very important for the outcome of our models. We use a quite simple model. It's a Gumpert kinetics, and we have a maximum yield that we put in, that we get from literature and our own lab experiment. And we have a kinetic factor which determines how fast we get our gas. And as you can see, there's a huge difference of the curves for the different retention time, how much gas we get. So the easy degradable waste products, they are here, and you can see there's very little difference about the retention time. Our slowly degradable stuff, as the cattle manure, the straw, and solid cattle manure, we can see there is an impact of increasing retention time. When we store our manure in the reference scenario and the digestate from the biogas plant in our biogas scenario, we use some model that we developed many years ago, which is yeah, I'll not go into detail with that. That's very technical, but it's determined, the rate is determined very much by temperature and some constants, and this Arrhenius fraction, and the volatile solid, which is organic part of our biomasses, are divided in a digestible, easy digestible part and a slowly digestible part, where the slowly digestible part means very little. And when we have digested our material, this volatile solid digestible will be almost limited to a very low level. So that's why we see a reduced methane emissions from our storage. Here you can see how much the emission is per tons of biomass stored in the different scenarios. And you can see the blue The blue one, that is the methane during the storage, and you can see that it has a huge reduction in the emissions because the relations I talked about. Looking at nitrous oxides, both during storage and on field, we see almost no impact on biogas. They are almost the same before and after. And the knowledge is still not completely well in this area. So, but from the literature and our own studies, the effects of nitrous oxide are very limited. Then when we have a biogas plant in Denmark, we often have quite a lot of transport because we have very huge plants, and because of that, we have an extra transport when we make a biogas plant, and for the liquid part, the cattle manure and the pig manure, we have we have calculated with an average driving distance on 20 kilometers back and forth, and on the solid manure a little more, and a little different for the other biomass, and especially the waste products. Usually we have a little longer distance, and especially the glycerol, which is to a large extent imported from other countries, we have a quite long transport. Most of it is transported in 38 tons trucks, so that means that we can reduce the emissions quite a lot because we have quite efficient transport. Looking at the energy balances on a pure energetical point of view, we can see here our plants and plus minus recovery of the heat, and you can see the gray one here, that's the process heat. That's the main negative consumption we have. As you can see, transport and electricity for our process is very low, and even though we have quite some transport on an energetical point of view, it's very, very little. And we have some very positive energy balances for all the plants. For the straw plant here, we have a very high energy production, and as I said in the start, it's not a plant that we can find in Denmark today. All the rest of the plants we can find, but this is a more theoretical plant because it has a very high load of dry matter, and the technology is not completely developed for this. You can read in the report more about the assumptions we made for all these calculations. So the greenhouse gas effects is the main outcome or the main reason for making biogas from the start. That is to reduce the CO2 emissions, and you can see the 5 plants here, and you can see here on the different things. I took all the nitrous oxide here, and you can see they are very, very small, hardly any effect of that. But looking at the main things adding to the balance, that is gas to the grid. That's the most important one, accounting for more than 70% of the total positive impact. That's the produced energy. The next one, that is the reduced emissions of methane during storage. And the red dots you can see here that we are in the range for these different plants from around 62 to 112 kilo CO2 per tons biomass that we add to the plant. Looking at the negative things here, one of the one that counts very much, even though we only account 1% leaks of methane from the plants, it accounts very much. So losses from the plants are really important. Carbon sequestration, we have a little negative impact on that also, but it is quite little By far, most of the carbon is conserved. When you look, we are looking at a 20-year horizon of carbon in the soil. And in that perspective, biogas has only a slight negative impact on it, because it's only the easy degradable carbon that we remove in the biogas plant, and the very recalcitrant carbon remains. Then, of course, we have some negative things from the transport, and process heat is the mainly negative one on the energy side. But again, transport means very, very little on the total balance. One thing that we didn't include in our study was the ILUC. That means land use changes. If we take out land for cultivating maize in Denmark, it eventually will have some consequences when we take out land that could be used for food, for energy. And EU study indicate in the range of 70 kilo of CO2 equivalent per tons of maize. And since we add 12% maize, that will reduce our balance with around 8.5 kilo if we included ILUC. So this means that doing that, the energy crop scenario would be by far the most non-favorable scenario. The impact of technology, that means hydraulic retention time, is one of the factors where we really can affect things. You can see here that increasing the retention time, that will increase our total positive impact. As you can see, especially the manure-based and the straw-based scenario, we have quite some important positive impact. For the plants with more easy degradable stuff, the positive impact is quite limited. The reason, of course, is that we get extra gas by this extra retention time, and we have less methane during storage. But the reason why we can actually even get negative on the hydraulic retention time, that is because we need a little more process energy, because we need bigger digester where we have higher energy loss. But it's quite a limited effect that we see from the retention time. But when we look at when we do research in the field and so on, we often see much higher effect. So that's maybe our model is not accurate enough on this parameter. Methane loss was really important. In Denmark and in the Danish biogas plant, we have examined this, and we see leaks. And we started in 6-7 years ago to measure it, and there is of course some diffuse sources arising from different places. Then we have the ventilation. That is mainly when we ventilate our pre-tank and so on. There will be some losses from this. And one very important factor here is also when we upgrade gas. The different technologies has different losses of methane, and we chosen the amine technology, which has a very low loss, and that's why we can go down to 1% loss in total. For other technologies, we have higher losses, and it can be quite hard to reach the 1% goal that we have in the sector. So as a total, already in 2015, we recorded around 2.5% loss from the Danish biogas plant, but a lot of initiatives was taken, and today the goal is around 1%. And for the plants that is in this voluntary program we have now, they are actually very close to this. And that's why we believe that we can use that as a good estimate. But when we look at the total energy balance with increasing losses, it's reduced dramatically, mainly because we have this high greenhouse gas effect of methane, and to a more limited degree because we have a little less production. But when we go to around 15%, this is model plant 1, it looks different from the other plants, but around 15% we are in zero. this will mean we have no gain at all by biogas if we have 15% losses. I'll tell you about the ammonia evaporation, because we have in Denmark regarded that ammonia emission during both spreading and storing of our manure and digesters was similar if we had biogas or we didn't. But we have experiments now that we often have a higher ammonia emission from biogas plant compared to manure that is not treated, and that's because we have more ammonia, we have higher pH, and with high amounts of straw, we are also starting to have higher viscosity. So this is a challenge we are facing. And when we look at emission from pig slurry and emission from biogas slurry, we can see that when we spread with trail hoses, which is needed in Denmark as long as we use it on winter wheat, for example, we have an increased loss by the digestate. Only when we inject into the soil, we are safe, because here we have very, very low emissions from both. But since we are spreading around 40% of our manure on winter wheat, we have a challenge here. Looking at the 5 scenarios, here we can see the two bars. First bars are the storage losses, a little higher for biogas. That's because not all our tanks are stored with a membrane. We also have some with crust, and there the biogas, because of the high pH, is a little higher. But it's mainly during the spreading we have this negative effect of the biogas when we spread it with trail hoses on winter wheat. And therefore, in all the scenarios, we have a higher emissions of ammonia. So that's really a challenge what we are working hard on finding solution on. And the only way we know today is that we need to incorporate a higher share of the digestates in the crops and shift towards crops where we can inject into the soil. We have also other nitrogen losses, that is nitrate leaching, and here positive on this bar means that we have less leaching. So the nitrate leaching are considerably reduced by anaerobic digestion, because we have a conversion of organic nitrogen to ammonia, which will not leach and be taken up by the plants very fast. So that is very positive for the biogas sector, except for the energy crop scenario, because when we grow energy crops, we will have some nitrate leaching from these areas, and we will have more nitrate from these crops on others. So here we will have hardly no effect when we include energy crops in the plants. For the organic farm, organic biogas, we have a huge positive impact by removing some grass from some areas to the biogas plant. Again, the ammonia evaporation here is negative. The NOx from transport, yeah, you can hardly read it on the figure, but of course, NOx is a pollutant which should be regarded, but still at a very low level because of the very advanced trucks that is used with very low NOx emissions for the new. I will go to the conclusion before I use all my time. I think I already used it, but we have around 65 to 106 kilo CO2 equivalent per ton of biomass. We have a very high impact of the straw plant, but again, we should be aware that this is still a theoretical plant. We need to have the heat exchanger to have a very high positive impact, and also to reduce storage methane losses. If we have higher temperature in our storage tanks, we will not have a good effect as we have calculated. The nitrate leaching, very positive, except when we add energy crops. And then we have the challenge with the ammonia that we really need to work on technical solution to solve this. So I'll end my presentation by this, and thank you for your attention. And I will stop sharing.
Thank you very much, Henrik. I think we got a few questions from Chris. For Henrik, I saw on your slide that methane leakage was quantified as 1 to 2%. Can you elaborate on this, as some here in the US quote much higher methane leakage rates?
Yes, it is.
And also to add to that, could you, because I can't really answer that question, the different upgrading technology. I know that amine wash is the main technology in Denmark now, but which other technologies have been used are used in Denmark right now?
So actually, water scrubber is still the most used technology, and a few one with membranes. So for this plant, it is a challenge to reach the low emission. It is possible technical to remove the methane from these technologies completely by RTO technology, but it's an extra cost, and it's not. I think it's done on a few plants, but still it's not common practice. But probably it will be needed to add this step in the future to reach the goals from the industry.
All right, let me see. Another one here. Do you expect that biogas plants will remain the primary technology for treating animal manure and organic feedstocks as Denmark moves even further towards its climate and renewable energy goals? So what's the role for biogas in making the Danish agricultural sector more sustainable?
So the biogas plays a very important role. We have, of course, other technologies that can be very important, but most of the other technologies, they rely on a biogas plant. For example, fast removal from the stables from pig manure is one of the cheapest technology today to reduce methane from the livestock production. But without a biogas, in the end of this, the effect will be limited. I still believe that biogas for a year to come will be really important for the treatment of animal manure. We have there is some limitation. We have a lot of manure being acidified to reduce ammonia in Denmark with sulfuric acid, and this manure we still don't have a good solution to take in the biogas plant. But other technologies like pyrolysis and things like that will not, at least on the raw manure, be able to compete for many years to come, I think. And hydrothermal liquefaction and so on, I think they are still way too expensive for long time ahead.
And I know there's a quite new study on the some sort of mission in the Danish biogas sector where it's important to have the manure as fast as possible to the biogas plant. Could you elaborate a bit on that, why and how that is being done?
Yeah, was part of the study myself, where we visited almost all the pig producers delivering liquid manure to biogas plant. They were visited, and all the statistic on how long the manure was in the stable and so on was recorded, and we took samples to measure how much the emissions was if during this storage, and there was a very positive impact and a very low cost around it. So it's really a low hanging fruit to improve the greenhouse gas balance for livestock. But again, if you just remove it fast from the stables, put it in a storage tank where it stays for 9 months, you almost lose all the positive impact. So you really need to have it connected to a biogas plant to have this benefits.
There's been some. I've tried to answer some of the questions in the chat. There's been a few questions with regard to composting in Denmark. Why that is not that big in Denmark compared to biogas? Could you elaborate a bit on that, Henrik, as well?
Yeah. We have hardly no composting anymore. Years back, we also had some composting plants on municipal solid waste, organic fraction, but we have several live LCA studies and so on it, and there's really very limited positive impact on the composting, and the biogas is a clear winner on a lot of parameters, on energy, on ammonia, on greenhouse gases, on all factors. Biogas has a much higher positive impact. So because of that, no municipality in Denmark today choose to do composting.
All right. I don't know if there's any other questions from the audience.
I could also elaborate a little on the household waste also. What we see in other countries is that we often see plants that is used only on household waste, so pure waste plants. We hardly, there's a few projects in Denmark on that, but by far most goes for co-digestion because it's an extremely cheap way compared to making a monodigestion of it, and it's much easier to make a good product for farming and higher acceptance from the farmers afterwards.
There is a question from Chris here. The quality program called Arlanda, that's a quality program for by far the biggest dairy company and dairy cooperative in Denmark. They were a bit reluctant to use organics and digestate from biogas on their fields. Could you elaborate what was needed to convince, let's say, the farmers and Arla to use that?
I guess it was a lot of measurements on heavy metals and xenobiotics and things like that.
Mm.
And yeah, it has been a little tradition in Denmark. So it was also a little they worried a little about consumer acceptance. That was probably one of the main reasons for a long period, because the Swedish partners they were allowing these byproducts in Sweden in the same company. So when they make the fusion, there was different rules in Denmark and Sweden, but now it's the same. So I think all the good data and on the very low level and the high quality in terms of heavy metals was the main factor.
Another question from Susanna Hunts. Could you point us to some scientific literature showing that AD is better than compost for climate based on full life cycle accounting?
We have at least a lot of Danish studies on it, a lot of Danish report from the Minister of Environment and so on. I'm not completely aware of some studies, scientific studies, but on the greenhouse gas level, it's quite easy calculations, and just looking in the ICCP and so on, composting has a lot of nitrous oxide and more methane and things like that. So yeah, but I'm not completely aware of any scientific studies that come in mind right now. But we can get the Danish literature, the Danish reports.
Of course, we have to emphasize that things are different in different countries, of course. Patrick Wood, have a question. Can you clarify what you mean by biogas application being surface applied? That sounds to me like it's applied to land, but I don't think that is what you mean. I think that's related to the use of digestate, of course.
Yeah. So we have two types of application of the digestate, and that is, in general, we should incorporate everything. That means by putting it below soil level to completely avoid ammonia emission. That is the ideal situation. But because we haven't really found the right solution for growing crops, for example, winter wheat, where we applied in May, all experiment has shown a really dramatic damage of the crops. So that's something we really work on, and my colleagues work very hard on how to do that. And unfortunately, we also acidify a lot of slurry during application. And here it's quite difficult with the digestate because it needs much more acid to go down to an acceptable level of pH. So it's really something that there is some intense scientific work on how to find good solutions for this.
So it's about applying the right environmental technologies in the right
situation,
I guess. How balanced is the final digestate in terms of nutrients? And if unbalanced, what kind of digestate post-treatments could be beneficial to produce concentrated fertilizer?
The digestate is not very good balanced. Often a little more balanced than manure itself, but it's not very balanced. It has way too much phosphor compared to nitrogen. So what farmers do is that they usually dose, or from the new regulation, they need to dose after phosphor, and then they put some chemical fertilizer on top of that. But we are in a phosphor excess in some regions in Denmark, and in the future more and more will be separated by centrifuges and screw presses, and the solid fraction will be transported to areas where we are in lack of phosphorus. So that's also something that's from legislation point of view, and there's happening a lot to comply with new phosphor regulation, which was set into place a few years ago, and which is very important for the biogas sector today to comply with that. And the biogas sector can help solving this problem, because the individual farmers, it's extremely difficult to find cost-effective technologies. But when you have big biogas plants, it's much more cost-effective to make a phosphor fraction. I think maybe that answered most of it, but that's mainly for the phosphor fraction, and that's what really we're doing most in at the moment, not so much on ammonia or on nitrogen right now.
Just to add to that, I know that one of the biggest players in Denmark are strategically working on producing what they call tailor-made fertilizer for specific crops, which and there's a need for that. I think that the farmers who also supply the manure to the plant, they are asking for specific fertilizer types. So that's one of the trends we see in Denmark. Let me see here from Maria. Would bioacidification be a solution for minimizing emissions from digestate application?
Bioacidification?
Yes.
Yeah. Oh, for the conventional farming, I don't think that's a solution. That's extremely costly, and it might be a solution for the organic farmer, but it's not something that is. There's been a lot of scientific study on it in Denmark, but it has not really not coming into the industry because of the cost, and it has not been possible to guide on how it can be done with low costs. So still too expensive.
Then there's a question: are you planning to jump from biomethane to hydrogen? And if I could answer that one, I think there are big plans for hydrogen in Denmark. The government just announced that they're going to build one artificial island which can collect basically all the power from a huge offshore wind turbine park. So there are talks on hydrogen. Definitely, a lot of money is invested in R&D, but also demonstration plants. And Henrik, you're also quite active in that space with the stuff you do at the campus on using CO2, for instance, for methanization. And
yeah, in Aarhus University we have done a lot of research in this area, and for sure that's a route that will come in future to increase the amount of methane that can be put in the grid and all this surplus electricity we have from the wind turbines. So it's really something that will boost in coming years, I expect.
And we also see the first plant using the first food industry, food factory using the CO2 for soft drink production. So there are different products coming out of the biogas plant that you can use. Let me see here. Is there a high concurrence in securing the feedstock since there's many ADs? There's a high tradition for the farmers becoming a co-owner of the plants, which makes them like they own part of the plant. They are in the interest of supplying them with the manure, get the digestate back for the fields. But there also a trend that the farmer is asking for a higher quality digestate and higher quality of digestate. Is there enough manure? I don't know, Henrik, could elaborate a bit on that? The biomass availability, basically.
Yeah, we have we can still increase our gas production very much. We are now at around 20% of the manure that is used, so there is a huge potential there. But it is the waste that will be limiting, and that's mainly from an economical point of view. That it will be a little challenging, and it's for sure, as you also said, Claus, that it is really the straw that is the co-digestion of manure with straw, which is what we believe will be the driving biomasses in future. And then it might be that we will have an increase, or we will have a development in making protein from grass, where we will have a lot of grass that could be used for biogas also. So that's a main biomasses that really can increase in future.
Thank you very much, Henrik, for your time and presentation and the insights. For me personally, it's always a playground to come to your site and see what you got going on in Follum. I'll leave the word to Cecilia just to close the session.
I think you have to unmute, Cecilia.
Yeah, I was just saying thank you very much to Claus for moderating this webinar, and for Henrik, because thank you for taking time to present the report. It's very interesting. You should all have received a link where you can read this report that Henrik has just presented. And as Claus said, that we also have the link for you to download our publication. I also put in my email in the chat box. So if you have any questions that we didn't have time to go through, please reach out to us and we'll get back to you as soon as possible on the email. Otherwise, thank you very much for your participation, and we hope that we will see you in one of our next webinars. Thank you.